Hi everybody! Welcome to the last lecture / review, since I need like another hour or so to finish all the topics. Thankfully what we're going over in chapter 5 can be summed up in like 3 ideas. Because I really only have like 3 or 4 questions from chapter 5 on the test. Because there's not really that much, so... Oh, you want to say hi one last time? Say hi. Say hi. There we go. Okay, great. Maya wishes you all great luck on the exam. Now get out of here. Go on. All right. Real quick, just as some final announcements for the last lecture day. Course evaluations due Friday on June 11th. Make sure you get those in. Lab worksheet is due next Tuesday. There is a Chapter 4 quiz. It's due next week. I just don't have enough space to write that on my screen. Check Canvas to see when the deadline is for that. Do note that the Chapter 4 will be covered on exam number 2. Also, that Chapter 4's quiz is open, which means that once you have finished it, it will immediately show your score and your answers, so that you use that to study. All right, let's talk about Chapter 5. Chapter 5 is about advanced theories of bonding, which might make you think, oh shit, we don't have any time to do advanced theories of bonding. Well, you're right, but you're also wrong, because there's not that many advanced theories. First of all, we're going to get rid of this. We're not going to talk about MO theory. MO theory is super cool. MO theory, ironically, is the topic they hired me to teach. I had to do that at my teaching interview, and they all later apologized to me. Because that was a terribly complex topic to hire a faculty member on. But I did fine, apparently, because I'm still here 10 years later. We're going to stick to these other 2 sections, which chops this lecture down to like 15 slides. And I'm going to go kind of fast, but what I'm going to do is when I get to something important, I will actually go to to this screen here, and I will point it out to you. All right, so the first thing that we want to talk about, and this is important, so we'll put it on this slide, so we'll call this the Chapter 5 important stuff. Important stuff. So covalent bonds form when orbitals overlap. All right. Now, what do I mean by orbitals overlapping? Well, what that means is that I literally put them in the same space, or at least as close to each other as I can. Now, we talked about this a little bit in Chapter 4, that you can't just jam the orbitals to be directly on top of each other, because then the nuclei of these atoms would superimpose, and that's no good. But on the screen here, you can see that we've got s orbitals and p orbitals. And what we're going to try and do is we're going to try and combine these in some way by just scooting the one on the left over near the one on the right and see if we get any overlap. Now, part of this is a visual illusion. Part of this is you have to imagine what is actually happening here. So with this first one, all I can do is make these overlap. But they totally overlap. Wow, that was a lot louder than I expected it to be. See, I had to put one in front of the other because I can't actually combine them. But if you imagine 2 spheres coming towards each other along the direction of the y-axis, this part right here, you can't see my cursor because I was clicked away. This part, get the arrow back. This part right here would be where they overlap. Now, if I did the same thing with this one along the y-axis, my sphere is going to sort of nestle in this little side pocket along the node. And so we would say, oh, this isn't going to overlap, and it totally doesn't. Same thing with this one, because we have a node on the y plane. The first one was xy, this one's zy. Or no, I'm sorry. The first one was ZY. This one is XY. So Y is involved in a node here. So me moving my sphere closer does not result in any overlap. But if I change the orientation of my p orbital so that it faces along the y-axis, since that's the one I'm moving along, this would work. So I can move my orbitals closer together, and certain combinations will result in orbitals overlapping, and some of them won't. So what we're going to do is examine those possibilities in more detail. Now, these pictures are a little more effective at showing where that overlap occurs. So here's my two s orbitals. The bond goes right there. So my electrons for my bond would go in this overlapping space, and they'd go here, and they'd go here. So bonds form when orbitals overlap. Covalent bonds, that is. Our electrons, one from each side, because remember, if I had two hydrogen atoms, it would be, this is how it would start, right? And these would then overlap, and so on and so forth. And this matches up with what we were saying earlier when we were drawing Lewis structures. The unpaired electrons form the bonds. Now, there is an interesting thing that can occur if I take two p orbitals that are parallel to each other, and I get them close enough. And that is that there's a region of overlap right here. Because remember that a p orbital is real fat, right? It's like a dumbbell. Well, if I put a second one like right next to it, you could see there's a region where there is overlap. Now, even though there are two distinct areas that the overlap occurs, we consider this to be one bonding region. Just like the top and the bottom half is one p orbital, the top and the bottom half of the overlap is one bonding region. And so if I put my electrons in there, they would go either on the top or on the bottom, but not both. I can't put a second pair here because that would be 4 electrons in a bonding orbital. So those are all the ways covalent bonds can form. They can form by head-to-head overlap of s orbitals, or an s and a p orbital, or two end-to-end p orbitals. Or I can do this side-to-side thing. Now, based on how geometry works, and you're going to see pictures of this in a little bit, the alignment of end-to-end occupies all the space between the nuclei. So if I drew a line straight through all the nuclei, for all of the orbitals in the boxed region, the overlapping area where my electrons would be goes through that line. So this line is called the internuclear axis. And in other words, I've just taken the two nuclei for each bond and drew a line through them. If your bonding region is in the internuclear axis, the type of bond that you're looking at is called a sigma bond. If the bonding region is not in the internuclear axis, what you have is called a pi bond. And that's the other important thing that we want to know. So we'll go over here and we'll write this down. So a sigma, or this, is along the internuclear axis. And then a pi bond is not along internuclear axis. So it goes up or down. Not sigma, sigma. There we go. Now, the area in which we have our overlap is going to have very interesting consequences for bonding. Now, when you draw a Lewis structure, the first bond between any two atoms must be a sigma bond, because that is the easiest place to put electrons, directly between two nuclei. However, that space gets occupied once you do that. If you make more bonds, further bonds need to be pi bonds. They have to go around the internuclear axis. And we're going to show that in 3 dimensions in just a little bit so you can see that. So here's your summary of what bonding looks like. A single bond would be a single sigma bond. But a double bond would be 1 sigma bond and 1 pi bond, and a triple bond would be 1 sigma bond and 2 pi bonds. So the first one is always sigma, any extras are pi. So let's do an example. Here is a molecule, and I want to count the number of sigma and pi bonds in the diagram. So I'm going to do sigma bonds in blue, and I'm going to do pi bonds in red. Now, obviously, this is not easy to do on a screen. So if you have like a print screen utility or something like that, when you get a question like this and you can just take it over to mouse paint or whatever and draw all over it, that helps. So here's what I do. Okay, I'm looking for sigma bonds. So I'm going to do the first bond. 1, 2, 3, 4, 5, 6, 7. So I'm going to indicate that. And then I'm going to change color. And then I'm going to count pi bonds. Pi bonds are all the remaining double and triple bonds. So 1, 2. So this molecule would have 7 sigma bonds and 2 pi bonds. You probably didn't think that on the last day, the topic that you're going to do required you to just do counting. And that's it, right? But yeah, this is where we end. We end pretty easy. Chapter 5 is relatively easy compared to all the shit we've done before. All right. Now, we've already talked about this. If you have your nuclei too close together, the nuclei repel. But if your nuclei are too far apart, they don't overlap and you don't make a bond, right? So there is some bond distance that is optimal in terms of, oh, if I get these any closer, repulsion takes over. And if these are any farther apart, my overlap is insignificant. And so this is where the bond length comes in. The bond length is an energy well. In other words, all bonds are just energy wells, where your electrons they sort of just fall into the lowest energy thing possible. That's right. So the s orbitals would overlap with the sigma as a sigma bond, and then the p orbitals do the side-by-side thing. Now, there is an extra catch to it that we're going to introduce in just a second that you totally don't need to know the theory behind. You just need to know, oh, this is what happens. Because we're going to see that in just a second. So, first of all, let's talk about valence bond theory. Valence bond theory is the theory that, okay, well, if I had my Lewis structures where I did stuff like this, so here's my selenium, and then here's my hydrogen, for example. Okay, I'm going to use the unbonded electrons to form covalent bonds, and then the ones that are bonded will just be how they are, right? So I'm going to assign these electrons. Now we're going to put those in orbitals. So if we have unpaired electrons in our electron configuration diagram, we can see where those will end up. And this is actually really elegant. So I'm going to show you this for H2S. So here is H2S. Hydrogen only has a 1s electron. Hydrogen only has a 1s electron. Sulfur has 1s2, 2s2, 2p6. We don't give a shit about that. That's not valence. But here's the valence shell for sulfur. And what we would say is, okay, well, sulfur's got unpaired electrons. Hydrogen's got unpaired electrons. Let's combine these things together. And so what I would do is I would say, okay, well, if this is my sulfur atom, I've got my 3s orbital with its non-bonding electrons. And then I've got a p orbital in the x direction, which also has non-bonding electrons. A p orbital in the y direction, which has a single electron. Actually, let me put that on the other side here. And then a p orbital in the z direction, which would be kind of like this, in front of the other things. And it has a single electron too. So that would be what sulfur looks like. I'm not great at drawing these on PowerPoint, but you can see there's my s orbital and my p orbitals all superimposed on top of each other. And then all I do is take my hydrogen and put my hydrogen right here. So here's H, and here's an H in the back. Something like that. That would give me the bent configuration that I want, right? And so it looks really elegant, except there's some issues here that you've probably already seen. You might have thought, well, wait a second, hold on. I thought bent was 109.5 for tetrahedral. Yeah, you're totally right, right? So there's my Lewis structure based off of what this is. There's my unpaired electrons. I've circled them. And this is a really simple way to understand why bonds form from unpaired electrons in each thing. So naturally, it's totally wrong. I had hoped that that would have been a little louder, so hold on, let me see if I could do that again. There we go. Yeah, so this is total garbo. Like, I don't even know why they have valence bond theory in the textbook. It's like such a fucking waste of time. I teach you this slide and then I say, nope, it's a coincidence. It doesn't work. That's all. Wasted your time. And you know, it's great to waste time, you know, on the last lecture. So this is total BS. This is not how bonds form. And there's a very important reason that disqualifies this, because this looks like it should work, right? I'm pairing electrons in the Lewis diagram. Let's pair them in the electron configuration. But when I drew that picture on the board, you probably noticed that all of my orbitals were at right angles, weren't they? So these are all 90 degrees apart. A tetrahedron is not a 90-degree system. This angle right here is 109.5 degrees. But all I can get out of this system right here is 90. So they're all 90. So it becomes impossible for this to be how bonding occurs. And so what we have to do is figure out what the hell is going on. And the answer to that is we cheat. Our model doesn't work. Okay, we're going to throw it out. We're going to just make up a new model. And that's where hybridization comes in. Hybridization is basically us saying, we don't know what's going on, so what we're going to do is we're going to do some math, in quotes, and make this work. And so what we're going to do is we're going to make a table here. All right, and I'm just going to fill this in real quick. So we all know what Vesper geometry is because we talked about that in the geometry lecture. That was on Monday. So if I write down these numbers here, well, if I spell linear right, trigonal planar, 4 is tetrahedral, 5 is trigonal bipyramidal, and then 6 is octahedral. All right, I'm going to put a code for each of these. And if you are watching this lecture and you're like, wow, I don't have any idea what the fuck is going on with hybridization, it's just he's going over it too fast. Remember this code. Because at the end of the day, all you need to know is if something is sp2 hybridized or sp3 hybridized. I'm going to try and tell you what that means, but on the quiz and in the future, people are just going to make the assumption that you know, oh, okay, the s and p orbitals don't exist in bonds. They blend together to make a hybrid. And if you just go, okay, yeah, hybrid, sure, and nod and go along with it, that's generally good enough. Because unless you're a physical chemist, then that's not good enough and you need to know more about it. But we're not physical chemists. We're general chemists, right? We're just learning. So I'm going to give you the foundation and that'll be good enough. So if you have a linear geometry around an atom, that atom is sp hybridized. If you have something trigonal planar, it's sp2. Tetrahedral would be sp3, etc. Okay? So remember the code and remember the Vesper geometry because they are inextricably linked together. Note that this is Vesper geometry or electron geometry as your text calls it. Not molecular geometry because molecular geometry has other shapes in there that could get you confused, although one of the shapes is the ones in this list. All right. That's the second to last thing I need to tell you, and I might as well write down the last one while we're talking about it, which goes up here. And we'll put it in blue. So sigma bonds rotate, pi bonds don't rotate. I guess I should put. There we go. We'll talk about bond rotation. This is literally it. This is chapter 5 right here. This is all you need to know. Hooray, we're done. But I'm going to actually do the lecture. So this is all that you need to know. So if you like hit print screen and upload it to Discord, like whoever's been doing that, thank you. It saves me the trouble. Cool. This is all you need to know for chapter 5. Just have this worksheet and you'll get 5 out of 5 on all 5 questions or whatever that chapter 5 is. And I'm telling you all this because it's the last day. It's important, but it's so minor after everything that we've done. All right. Let's look at carbon. I'm going to go return to valence bond theory real quick. So we'll just throw 1s in here for carbon. So carbon has 4 valence electrons. 1, 2, 3, 4. And so what this says is that I should have a molecule that looks like this for carbon. This would be what valence bond theory suggests. Oh, you could just do this with carbon. And you totally can't because that doesn't follow the octet rule. We've already talked about how carbon loves to form 4 bonds. And when I drew my Lewis structure, I started like this. So why the fuck are these paired? Where did this come from? I want this. This is what I want. How do I make it like that? Well, what if I could do the following? So let's erase this monstrosity. And really, if this is my valence shell right here, 2s and 2p, the only thing that's preventing me from getting 4 dots is this frickin' thing right here, this 2s orbital. What if there was a way to unpair it? And the way to unpair it is to say, okay, what if, for some reason, this happened? Because remember Hund's rule from Chapter 3. If all your orbitals are equal in energy, then you just do this. You put one at a time, right? And nobody gives a shit about 1s. So if I could do that by supplying carbon with just a little bit of energy that it would get back by making 4 bonds instead of 2, then I can rationalize this as a thing that happens. And this is called hybridization. So what happens in hybridization is that we take our original orbitals, these are called atomic orbitals, and we hybridize them into hybrid orbitals. And then we give them a name. How many things did we hybridize? Well, we'll take the felt tip pen here. We'll go like this. Well, I put in an S, and I put in a P, and a P, and a P. sp³, because there were 3 p orbitals with my s orbital. Get down from the table. My cat just jumped up on the desk and yelled in my ear. Not okay. Now, if I hybridize my orbitals, then I get the 4 unpaired electrons, which is what we predict when we draw the Lewis structure for carbon, which is what we've been doing all along. So now our model matches our observation. Stop. Oh my goodness, now everything is falling apart. Everything is falling on my lap, and this is obnoxious. There we go. All right. So now my slides are going to do basically what I just wrote on the screen here. So hybridization is just a model that predicts, oh, okay, we're going to do this thing I made up so that I can unpair all the electrons. And in reality, this is actually what happens. So our orbitals are all equivalent energy in a bond. So if I look at CH4, I end up seeing that there are 4 bonding orbitals, all of the same intensity and strength and length and stuff like that. Now, if I draw a picture of that, I'm trying to find my picture here. Hold on, we'll come back to that. Here we go. If I draw a picture of that, we get new orbitals with new shapes. So if an s orbital looks like a ball and a p orbital looks like a dumbbell, an sp orbital or sp2 or sp3 or however many you combine in there looks more or less like the average of those. So we get these sort of bowling pin looking shapes out when we combine these mathematically. You do not need to know the math behind that because even I don't know the math behind that. But you can kind of see that ball plus dumbbell averages out to something that looks sort of between a ball and a dumbbell, right? Which is why one end of the sp3 orbital is larger than the other, because that's where the ball ends up on average. Now, when I combine all 4 of those together, they all overlap conveniently in a tetrahedron, because there's 4 of them. And the optimal way to arrange 4 things around a central point is to shove them around a tetrahedron. Now, these little lips on the end here, like this right here, they still exist. However, most drawings will ignore them. So if you're wondering, like, where's the little lip? Where's the top of the bowling pin? It's just omitted. For whatever reasons, that's just what we do. And now, when I make my bonding, with my carbon, these electrons being the ones that belong to carbon, we'll highlight them right here. And then the ones that I'll do in red. Wow, I really should have done red and purple. That would have been a great time for this. The red ones belong to hydrogen. So now we can make molecules that match the geometry we observed because we hybridized. So that's the gist of what hybridization is. For the rest of the lecture, I'm just going to... So I'm going to quickly go back. Let me look at this. There's nothing else that I care about on here. Well, actually, I care about this. Only molecules have hybridized orbitals. Individual atoms have their original electron configuration diagram that we talked about. So you do not need to hybridize for just carbon by itself, nor do you need to do that for hydrogen by itself or oxygen by itself, etc. But once they start making bonds to stuff, you hybridize. All right, so the rest of this is just going to be pictures. If I asked you to draw the number of sigma bonds in this, then the way that we would calculate that, there's one of two ways. So you could say, oh, okay, well, if I draw a line between each letter C and letter H, my electrons that I just drew in there are along that line. So they must be sigma bonds, right? They're on the internuclear axis. The other way to do it is just draw a Lewis structure, yeah? And remember that the first bond, sigma, 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 sigma. What is this, Mega Man X? So this has 4 sigma bonds. All right. Now let's look at nitrogen bonding with ammonia and see what happens. So here's my diagram for nitrogen. But I need to hybridize to get 4 sp3 orbitals around the nucleus, because I need those orbitals to go in the arrangement of a tetrahedron. So I'm going to shift these so they're all the same energy. And this is what happens. My nitrogen atom already has a pair of electrons, and it has 1, 2, 3 unpaired electrons. So it will make 3 bonds, and the 4th position will be a pair of electrons, and that looks like this. Oops. I mean, I guess I'll draw the picture for you. I ran out of space, but we'll do it over here. So if I was going to draw this, so I would draw my nitrogen, and then I would draw 1 balloon, 2 balloon, 3 balloon, 4 balloon. There you go. So there's my nitrogen in the middle. And so I would have 1 electron, 1 electron, 1 electron, pair of electrons. And then what I would do is I'd bring along hydrogen. Hydrogen is just this, right? So I'm going to just put 3 of those right next to it. So here's my hydrogen, H. Here's a hydrogen, H. Here's a hydrogen, H. And that's what ammonia would look like. Perfect. Okay, let's get rid of this. I might need the space later, and while I'm thinking about it, I really should be drawing on a different layer so that I don't accidentally go like, wow, 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 wow. And everybody hates me because, no, we need that. So, new layer. Boop, there, done. Now, how do you make a double bond when you hybridize? So we already said that the double bond occurs in the overlapping region, right? So this is one region. So the way that that looks in the model is in the following way. So in order to make a double bond, I need p orbitals. Orbitals for double bond. So to make a pi bond, really what I should say here is for pi bond, not double bond. Also, I should put this felt tip pen away because it's obnoxious. In order to make a pi bond, we just don't hybridize our orbital that we're going to use for it. So for instance, if this is my structure that I'm going to make, I need a pi bond right here, right? So I need to save a p orbital for the pi bond. Have you figured out why it's sigma and pi, s and p? Doo-doo-doo. Very clever, right? We'll just change the language on them. They'll never know. It's all Greek to non-chemists, yeah. So if I hybridize only 3 orbitals instead, and I just leave this p orbital available because this is how I'm going to make my pi bond, and these will be my sigma bonds. Now the orbitals that I make have a different name because I only hybridized sp³, sp². So the label or the code that I gave you at the start is just how many orbitals are hybridized. sp3 is all the s's and p's in the valence layer. sp2 would be, oh, I saved one of those p orbitals. I needed it for a pi bond. sp would be, oh, I needed both of the pi bond orbitals available, so I saved 2 of my p orbitals. And so on and so forth. What's the optimal arrangement for 1, 2, 3 things around a central atom? A triangle. And so that's what you see right here. So here's my triangle. And then the p orbitals go above and below the plane. So here's my p orbital. I'm going to draw them exaggerated so that you can see where the overlap would be. Okay, maybe that's a little exaggerated, but that's okay. So there's where my overlap would be, right in this region right here. Now, some diagrams don't do that. What they instead do is they do this like teleportation thing with the dotted lines between them, because they just space everything out so far for the purposes of illustration. So note that these atoms this carbon atom and this carbon atom are actually much closer to each other, so that there's a lot more overlap in the middle, so that these orbitals, which are actually wider than shown, would overlap. And then finally, we can do that with SP. I'm not going to have you do these examples because we don't have time. I'm going to come back to bond rotation just a second here. For SP, I'm going to save 2 of my p orbitals so that I can make a linear arrangement. And so you're probably thinking, oh, okay, well, I'm going to have, here's my linear arrangement of orbitals. So one's going to go this way and one's going to go this way. And then my p orbitals, one will go up and down, and the other will go front to back. And that's exactly what happens. I personally like this diagram better because it shows where the pi bond occurs. But this is what the bonding would look like for sp. And so you could see that here's the p orbitals. So this one in the back here. And then we'll just get a different color here. Here's one on the top. The one in purple is the sp hybridized orbital. I know it looks a lot like just a regular old p orbital. But instead of one orbital covering both sides, the left and the right in this diagram, that's actually 2 separate sp orbitals. The remainder of the slides, you can actually look at this if you just want to see sp³d and sp³d². The logic is the same. It's just that for anything that has 5 and 6 bonds to the central atom, it's a third a row element or further. So you have d orbitals available, you hybridize those, and they look like this. So these orbitals right here would be sp³d, and then these right here would be sp³d². And really all the model is doing is it's just saying, okay, what was the geometry around the central atom there? I'm going to make a balloon that points in every direction. So you might hear these referred to as balloon diagrams. All right. Last thing for chapter 5. We're going to go back real quick. And it's this slide right here. Because sigma bonds are the result of orbitals overlapping, so if this is my nucleus and this is my other nucleus, if I were to rotate this around the internuclear axis, those guys would stay overlapped. You can imagine, like, if two people are shaking hands and you spin one of their hands along the axis of their arm, like, they won't be shaking hands anymore, but their hands will stay enjoined. All sigma bonds have bond density over the internuclear axis, and because the bond just relies on those orbitals staying overlapped, sigma bonds can rotate and spin. That has some interesting consequences. Namely, if you have a molecule and you draw it in the same connection but a different orientation in space, you either get the same result or a unique result. In this case, since this can rotate down to this position and then everybody shifts up one, these two things are the same. But what about these molecules? Well, if I draw in my pi bond, my pi bond becomes a double bond when these overlap. But if I were to twist this guy down and this end would come up, then what I would end up having is something that looks like this orientation, right? Yeah, isn't shear stress great? Now with double bonds, you totally are just torquing the bond out of position, where my overlap would be top to bottom, but now over here, they don't line up, right? So if you try and rotate a double bond, it would break. And since molecules want to stay in the orientation that has the lowest energy, which is in the bonding orientation, making a double bond locks the molecule's configuration in place in terms of where atoms are. So this does not have the ability to swap places with this one. So if I have this molecule and this molecule, they are unique. Even though they have the same formula, they have different geometry. And you may have heard these words before, cis and trans. I mean, it's Pride Month, right? So we got to talk about that. All cis means is that these are on the same side. Trans means they're on different sides. And when we get to naming in organic chemistry, we're going to apply the name cis and trans for, okay, what are the important atoms on here? I want to put them on either the same side and call them cis, or the opposite side and call them trans. And there you go, because we know what cis and trans are, right? That's where the words come from. They're just prefixes that describe that. There you go. This is the sound of me throwing the pen on the tablet. I don't know if you could hear that. There we go. It's over. Look at all the shit we're skipping. There we go. Boop. I guess we can go straight to this. Here we go. I mean, you guys do get your, like, hooray, it's done. Yay. Oh, goddammit, I ruined it again. Hold on. Yay. That's it. I told you I only needed 30 minutes. So, chapter 5, for some reason, like, why? Why make chapter 3 6 fucking weeks? And then chapter 5 is like, oh, it's an afterthought. Whatever, right? But that's it. That's all there is to chapter 5 that I care about. So, let's see. And it's 1 o'clock. So, what we're going to do is we're going to do this. And we're going to take our 10-minute break. And when we come back, we're going to review whatever the hell you want to. Totally up to you. So let me start up the music again. Yes, you're going to have to hear the Wii Shop for 10 minutes. I personally like it, so haha. Hi, everybody. Do 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 do. Do 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 do. Do 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 do. Do do do. Okay, there's enough of that. All right, so on the screen is the hybridization and chapter 5 stuff. So make sure that you're. Oh, it's gone. You can always go back in the video. That's why I get to be like a little bit of an ass. With like, I hope you wrote it down. Oh, it's gone. Because like you just hit pause and rewind like a second or whatever, right? Okay, so this is now a review session, which means you can ask me anything you want about the class. Topics to avoid asking me stuff about, unless it's directly relevant to a question that's on the test. Don't ask anything from chapters 1, 2, or 6, because it's not tested. Like, obviously, you can't just ignore sig figs or units or whatever, but the test is strictly on content after the last test. So, sections 3.1 and 3.2, which is all the math stuff that we talked about that was before on the first test, not going to see it on the second test. How do I do Chem 161? Sign up for my class in the fall. That's how you do it. If you're asking me that at this point, enroll in the fall. But for more specific questions, I'm happy to answer them. So there was a question about formal charges, and so we can look at that in more detail. So I'm going to do your peroxide example that you asked me about first. So I'm going to try and draw peroxide correctly here. So here's an oxygen, here's an oxygen, and here we go. Yeah, we do nomenclature. If you have more specific questions about nomenclature, I can answer those, because a crash course is sort of just like we would be redoing everything we just did. So remember that formal charge is number of valence electrons minus number of current electrons. And that for current electrons, we're going to count bonds as one electron because the other electron is being shared by the other entity, and we need to count it over there. Because we don't want to double count electrons in formal charge. And so the way that we do that is we circle an atom in question. So I'm going to just pick this hydrogen here. And hydrogen has one valence electron, and it also has one electron that it has currently in its domain. So its formal charge would be 0. If I picked this oxygen instead, whoop, there we go. And I calculated its formal charge here, I would have, okay, 6 valence electrons, because that oxygen starts with 6. And then I have 1, 2, 3, 4, and then 1 bond, and then 2 bonds. That's 6, so this is a formal charge of 0. And the other oxygen and the other hydrogen are all exactly the same. So hydrogen peroxide, not super exciting in terms of formal charges. But what if we just look at the peroxide ion itself, and I get rid of the hydrogens here? So let's do that and see if anything changes about this. Oops, I'm on the wrong layer. So here's the peroxide ion. And now let's calculate the formal charge for these. So I'm going to just circle one of them. Whoop, there we go. So oxygen still starts with 6 valence electrons, but how many does it have now? 1, 2, 3, 4, 5, 6, 7. So the formal charge on this oxygen in the peroxide polyatomic is -1. And if I do the same thing over here, I get 6 minus 1, 2, 3, 4, 5, 6, 7. I also get -1. And if I sum the formal charges together, I get the actual charge. So the sum of the formal charges equals the total charge. And that's universally true. When you do this, if you're checking your work to make sure you counted your formal charges correctly, they should sum together to give you the total charge of the molecule or ion. Now, if the total charge is 0, then you should have the same number of positives or negatives, or ideally everything has a formal charge of 0. Remember that your goal is to have your formal charges as low as possible if you have options for making double bonds. Yeah, the exam is just chapters 4 and 5. Well, no, actually, sorry. 4, 5, and 3.3 onward. So chapter 3, chapter 4, chapter 5. I mean, we spent like 5 weeks on chapter 3, and only one of those days was before the exam, so I can't just say, no, we're done with chapter 3. That one's written off. I don't respect your time. Really, I put it on chapter 3 for your benefit, because I respect your time. Yeah, okay, well, we all know that that's bullshit. I have to test you on chapter 3, because that's my job. Alright, so that's peroxide. Let's look at something like carbonate, because that was also asked for. So, boop. And then we'll get rid of this right here. Boop. Alright, so if we're going to look at carbonate here. So, by now you should be able to draw the Lewis structure for carbonate, and it looks like this. The overall charge is 2-, so that's a good indication of what our formal charges will sum together to be. So let's start with carbon here. Carbon is in group 4. It has 4 valence electrons. Sorry, group 14. It starts with 1, 2, 3, or I'm sorry. It starts with 4 electrons. It has currently 4 electrons around it for a formal charge of 0. And then I can start looking at other oxygens here. So I'll pick this one. So this oxygen starts with 6, but currently has 1, 2, 3, 4, 5, 6, 7. This oxygen over here starts with 6, but currently has 1, 2, 3, 4, 5, 6, 7. And then this last oxygen up at the top here, 1, 2, 3, 4, 5, 6, because it has the double bond, it has a different formal charge. But you can notice that, oh, okay, I have a negative and a negative, so I have 2 negative. So all the math checked out. And you can apply this to any molecule that you want to. Now remember, your goal is to minimize the formal charges. That gives you the best structure. Now in this case, we could just make more double bonds to carbon, but then we would exceed 8 total electrons around carbon. Remember that elements in period 2 cannot violate the octet rule. They don't have access to d orbitals to do that. Apparently there's a van outside my window beeping, so I apologize if you heard that. So in nitrite, nitrogen would have a formal charge of 0. We can check. Let's do nitrite real quick. So nitrite is NO2 minus. All right, I believe that that's right. Let me count those again. 6, 12, 17, 18. 16, or 8, 16, 18. Yeah, there we go. So here's the structure for nitrite. And we got to do this to it. And so if I formal charge this oxygen on the left, I get 6 minus 1, 2, 3, 4, 5, 6. We get 0. If I formal charge this nitrogen in the middle, I get 5 minus 1, 2, 3, 4, 5. Also 0. And if I formal charge the oxygen on the right, I better get negative 1. 1, 2, 3, 4, 5, 6, 7. I totally do. So that's nitrite. In nitrate for NO3 minus, nitrogen actually has a positive 1, and then 2 of the oxygens have a negative 1 to give you a total of negative 1. And you can't do much better than that because making a double bond to the nitrogen to reduce the formal charge would actually exceed the octet rule. So nitrogen's just kind of hosed in that situation. It got a real bum end of the deal forming nitrate. And then oddly enough, nitrates are super common. So who knows? Elon, if you wanted anything to do with nomenclature, can you give me a more specific example? Like, can you narrow it down to like a type, as opposed to, hey, can you do the nomenclature lecture again? Because I can't do that in 20 minutes, which is most of the amount of time that we have left. Where was the point that we no longer do math? At the start of this, after exam 1. So you don't really need a calculator for exam 2. I mean, obviously you can have your calculator handy. I just don't think that you will reach for your calculator unless it's to do something like, oh, okay, here's the molecule we were given. What's 4 plus 6 plus 6? Like, yeah, you could type that in the calculator if you want to. But no math on this exam as far as I'm aware. There will be math on the final, obviously. Since the final is chapters 1 through 6. Quick refresher. I don't really know how to do a quick refresher for nomenclature, though. That's the thing. It's like we do it in 2 days because it's a short topic, but it's really dense. So I need more guidance, unfortunately. Like, I could write out the types of naming. So there's ionic and a subcategory of that would be polyatomic. So there's a set of rules. Then there's molecular. That's its own set of rules. And then there's acids. So if you know at least one of those two, so like if you review the names, not the names, but the schemes. So for acids, here, let me clear the screen real quick. I'm doing this multi-layer shenanigans stuff, so. Sorry, I'm writing and focusing here. And I'm like, wow, this is the quietest I've ever been. There you go. That's like for acids, I feel like if I was going to give a crash course, this is what I would write. Where ens and ide is the name of whatever it is you're working with. So like cyanide follows this pattern, chloride, nitride, sulfide, etc. 8 would be things like sulfate, periodate, hypochlor. Oops, that's wrong. Chlorate, carbonate, and then enzonite would be like hypobromite, nitrite, sulfite, phosphite, etc. That's what I think of when I'm naming acids. Is I just look at the suffix and I just drop it into the correct template. So electronegativity is the ability of an atom to pull electrons towards itself. And it's sort of like like if you were playing a video game, like an RPG, some of your stats are like basic stats and then other stats are like derived from others. Electronegativity is a derived stat. Like it's a bunch of factors conglomerated together to just give you a rating from 0 to 4. So electronegativity is defined as the ability of an atom to pull electrons toward itself. Now, typically, we use this in the context of bonding. Now, electronegativity is not an intrinsic property of atoms itself. It's actually derived from electron affinity and effective nuclear charge. So, atoms with higher electron affinities and higher Z effective have higher electronegativity. That's why all the elements on the left with low Z effective have low electronegativity. And then what is electron affinity? Electron affinity is a very strict thing to define. So this is the energy from adding one electron. So for example, if I had fluorine and I gave it an electron to make it fluoride, there would be some energy change associated with it, and that would be the electron affinity. I realize you don't know what delta H is because we haven't done thermo yet. Delta H is just energy released or gained from the transition that we just did. So if electron affinity is how much energy you get from adding an electron, electronegativity is just a scale on 0 to 4 of how good atoms are at getting energy released by adding electrons. Fluorine and chlorine are two of the best. Now, I'm happy to be more specific on these, so if you have other questions, like, please keep asking them. I'm just sort of talking about things that people ask me to the point where I think that's enough. And if you need more, I'm happy to go over more. Sorry, drinking my water here. Let me mute this. There we go. How do you figure out if a compound is ionic or covalent when working with more than 2 atoms? So, for the purposes of this class, if you were given something like, I don't know, something like that, then what you would be looking for are polyatomic ions. Or in other cases, like for example, if you had this, now the bottom example I would never give you on a test. However, that is a compound that we do work with in 162. Like, you don't have to name that. So if you see a polyatomic ion or you see metals in the formula, it's ionic. Oh, excuse me. If you don't see polyatomic ions, then it's covalent. Now be careful because there is a difference between this and this. So this is sulfite, and this is sulfur trioxide. So make sure that you are aware of the charge on the substance that you're looking at, because that does matter. Other questions? Yeah, you're allowed to ask about equations. I don't think there are any equations on this exam. It's all just concepts. Like, if we're not doing math, there aren't going to be equations involved, yeah? I mean, unless you have, like, an equation for the theory of everything, in which case, I want to know about it, too. But yeah, if there's no math on the exam, there's no equation that you need to know. Ha ha ha. That I can't answer without doing research, and that would take a second. Oops, that's the wrong thing. So, I can look into that, so give me a second. Can I go over molecular geometry? Sure, give me a second. Naming formula. Formula naming. I have a few questions on naming. So I don't actually have the ability to assign a percentage to that, but do make sure you understand the naming. Oops, just threw my pen on the floor. Ow, darn it. There we go. Make sure you can go in both directions. Like, if I give you a formula, tell me the name, and if you know are given the name, tell me the formula. Am I on the right screen? I am. Okay. What? So molecular geometry is kind of like the same question with naming. Like, can you be more specific about molecular geometry? Because I don't have enough time to completely teach you molecular geometry. Do you have a specific question about it? Or do you want like an example? Like I guess I'm just like, can you be more specific? How do you know the difference between bent and trigonal planar? Yeah, we can do that. So, oops, I'm on the wrong screen though. So, trigonal planar and bent are in the same family, but trigonal pyramidal is in a different family. So, remember that there are different families. So, this would be Vesper geometry. So linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Maya, stop. What am I stuck on? Oh, there we go. Okay. So that's Vesper geometry. Molecular geometry will take one of these and it'll look at possibilities for if my central atom has atoms bonded to it, or if some of those get separated out to become electron pairs. So this would be trigonal planar, but this is bent. because I have a double bond there. And then, for example, for 4 here, let me get a different color. For 4 electrons, I could have a central atom that has 4 bonded atoms around it, and that would be tetrahedral. Or one of those could be an electron pair, and that's trigonal pyramidal. Or I could have 2 electron pairs, and then that would also be bent. I need just a second, because the cat is going absolutely nuts. Oh my goodness, my stupid cat. She jumped in the laundry basket and couldn't get out, so she was crying. Go on, stop that. Oh. Now I'm spraying compressed air at her because the water bottle's on the other side of the room. So, that's molecular geometry. Molecular geometry is like a subset of your electron geometry. She's not a poor thing. She could have jumped out, but she didn't want to. She just wanted to climb in there and be obnoxious. Like, help, I can't get out. So I helped her out, and now she's upset with me. By helped her out, I scooped her up and put her on the floor, and she was like, how dare you? Cats are like having toddlers, I think. And I do not want to be a freaking parent. Hell no. I can barely tolerate my cats. It's considered unethical to squirt bottle your child if they are misbehaving, I think. Like, don't do that. Can you get the spray bottle? Also, I don't know about you, but if like somebody spray bottled me when I did something wrong, I'd be like, wow, that's refreshing and nice. Like, I love water. Water is great. That's my concern, is that my cats are going to be like, oh, we like the spray bottle. Maya hates water, but I don't think Kresnik hates it that much. So, all right. Other topics for review other than my cats. My cats will not be on the exam. And if I've already answered your question, and you have other like follow-up questions, please do ask them, because I'm happy to go into more detail. Because I could just hit clear and draw whatever you want me to again. Yeah, quantum mechanics is on the exam. So definitely know all of your quantum numbers. So know what n is, know what L is, know what m sub L is, know what m sub S is. Do we have to remember the angles? Yes, you do. So you need to know that linear is 180, trigonal planar. I could just write those down right here, actually. So linear is 180, 120, 109.5, 90 or 120, and 90. Why do xenon and krypton make bonds? Because they can. That's really all there is to it. Like the deeper reason is they have low ionization energy relative to the electron affinity of things like fluorine. So fluorine is willing to make bonds with them. Like normally things don't form bonds with krypton and xenon in like high Z effective substances because they would have to pull an electron away from the atom to make a bonding site. So remember, bonds can only really form from locations that have individual electrons that are not paired. But if you want an electron bad enough, you can rip it away from something like xenon or krypton if you're fluorine. Fluorine wants electrons so badly, you guys. You have no idea. It wants it so badly. It'll fight xenon and krypton for electrons. The short version though is just because it can. Like we have the basics of the idea of how to get to the why, but without doing any thermodynamics and me assigning numbers to it, it's very difficult for me to explain that. Like if we had access to numbers and we're going to do that 162, I could say, "Oh, because delta H is negative for that reaction." And then we would be done with that conversation. Because any reaction that releases energy is thermodynamically favorable. And for this particular reaction, that ends up being thermodynamically favorable against all odds. So you don't need to know about why that happens for this class, but if I give you a molecule that has a xenon or a krypton in it, just treat it as 8 valence electrons and add it to your pool, and draw the molecule the best that you can. All right, I'm going to call last call for questions here since we're going to run out of time soon. If you have any questions at all, let me know in the chat. That's a good question, actually. I need to look that up. So, when is the final exam review? Whenever it says on the syllabus, if it says it at all. Yeah, it looks like Tuesday is when we have our final review. So Tuesday the 15th. I'm just checking all of my syllabi now to see when my reviews are. Are they all on Tuesday? Yeah, they are. Why would I do that to myself? Oh, well. So the schedule that is upcoming is, so the exam on Friday, final exam review on Tuesday, and then final exam Wednesday. Yeah, you got it. So yeah, we have one more review session that we'll meet for before the final. It's the day before the final. And it will cover the entire class, the final exam. So you can ask me any question that you want among all the content in this course. How many questions on the final? 4,806. No, wait, sorry. Wrong final. Two questions on the final. What number would you like me to tell you to answer that question to your satisfaction? Like, I don't know. I don't know how any of this helps you. Yeah. Number of questions, not a useful question to ask. That's not going to help you. Time is more useful. I give you 2.5 hours for the final. For exam number... For exam 2, I actually changed it. I think I actually increased the amount of time. I have to look up time for exam 2, so... final is 2.5 hours. You do still get 2 attempts. Exam 2 looks like I give you 1 hour and 40 minutes. So 100 minutes, yeah. All right, if there aren't any more questions, we're going to call it a day here because we are out of time. I do want to thank everybody for coming to the review lecture. And yeah, that's a wrap. So we have covered everything that there is to cover in Chem 161. So there will be one final review lecture held next week during finals week. But other than that, yeah, that's it. So I hope that you found this class helpful. I know that at many points it was very stressful. But I do want to thank you for being a part of it. So thanks for coming to all the lectures, for being a part of the Discord channel, sending me email, whatever it is you did throughout the quarter to be a part of this. Thanks for just being a part of it. It's really hard to be an instructor for online classes, but having a community that gives feedback and is chatty and asks thoughtful questions, and like, I can tell you guys generally care about the class. I was going to say genuinely, but I actually don't know if that's true. So I just wanted to say thank you. And best of luck for you on the exam, and if all goes well, this will be the last time you hear my voice.